So this is part 2 of review of Green Book number 4 that involves solving trig equations, something we're going to do right at the end of the school year. So this is a complicated question. It's got a trig equation that's got a double angle in it, and it wants us to solve within the domain 0 to 360 degrees. So we know our answer is going to be in degrees. Anytime you have a double angle in a trig equation that doesn't have another double angle, we want to first make a substitution using a trig identity. Okay, so I'm going to rewrite this equation, but hopefully you can see that in place of what I have in red here, I've made a substitution. Now you have three different choices for the cosine of 2 theta. So the reason I chose this version of the cosine 2 theta, the one that only has sine in it, is because I have another sine expression elsewhere in the equation. I wouldn't want to mix in a cosine along with a sine. That just complicates things. Now that we've got it all in terms of a single trig function, sine, it's just a matter of me solving this thing. So I'm going to distribute the 3. Now I've got a quadratic equation. I want to get all the terms on one side so I can solve it by the quadratic formula. So I get it into standard form, but I don't really like this -6 in front. So what I'm going to do is multiply every term by -1, or divide every term by -1. Now I'm ready to solve this using the quadratic formula. I recommend when you're doing the quadratic formula to first work out the discriminant, the b squared minus 4ac. So when we do that, -1 squared minus 4 times 6 times -2, we get 49. That's good news. It's nice when the discriminant is a perfect square. That means we're going to have rational solutions to the quadratic. So when I substitute that 49 into the quadratic formula, remember the quadratic formula is x equals -b plus or minus the square root of b squared minus 4ac, which is that 49, all over 2a. So 2 times 6 is 12. This plus or minus forces me to split it up into 2 though. So I've got 1 plus 7, which is the square root of 49, over 12, and that simplifies to 2/3. Or, from the plus or minus, I've got 1 minus 7 over 12. That simplifies to be -1/2. Okay, so now I want to do the inverse sine of 2/3, and I get 42 degrees. And I'm going to turn this 1/2 into a positive half and do the inverse sine of positive half. So I get 30 degrees. Keep in mind though, those are just the reference angles. Okay? Because this is positive, I know my reference angles are going to be in the quadrants where sine is positive, 1 and 2. Because this ratio is negative, I know I want to have my reference angles in the quadrants where sine is negative, which are quadrants 3 and 4. Finally, I make my pictures. So, make out those sketches. We said in quadrant 1 and 2, I would have a 42-degree reference angle. Well, that's easy here. It's just itself, 42 degrees. In quadrant 2, the reference angle is red. Therefore, the angle in standard position is 180 minus 42 degrees. For a negative value of sine, we're going to be in quadrants 3 and 4. So the reference angle is 30, both cases. One angle in quadrant 3 is 210. The angle in quadrant 4 is 330. So those are our 4 solutions that are between 0 and 360, and I write them all out here to the nearest degree. In this question, it's sort of an application question. It says we've got a railroad tunnel opening modeled by this function. We want to first, it gives us 2 things. Part A, it says solve algebraically for all the values where the height of the opening is 6. So it's basically saying sub in 6 for f of x and do the math to find out what x is. And then give your answer in radians. And then there's a follow-up question, part B. wants to know the maximum height of the entrance of the tunnel. So let's do part A first. We're going to, as we said, we're going to sub in 6 for f of x, and then do the math. So right now, treat this sine of x as just like a variable that you want to get by itself. So we're going to subtract 2 from both sides, we get 4. We're going to divide by 8, and we get half. Now we want to get x by itself, so if you remember, we're going to do the inverse sine of half to get x. And x is a 30-degree reference angle. Okay? So 30 degrees in terms of radians is pi over 6. That's the only value within 0 to pi that exists. Part B of the question involves finding the maximum height. So if you remember from your trig graphs, the only things that affect the height of a wave are the amplitude, which is 8, and the vertical shift, which is 2. So in this case, instead of oscillating between 1 and -1, as it would if it didn't have any amplitude other than 1 or any vertical shift, it's oscillating between 8 and -8. But then it shifts up 2. So it's now going as high as 10. So we simply add 8 plus 2, which is the amplitude plus the vertical shift, and we've got our answer 10. Thanks for watching.